Okay, welcome everybody to HO Colloquium today by Nick Pedatella, who will be speaking on development and applications of data assimilation for whole atmosphere models. Nick Pedatella received his PhD from the University of Colorado in 2011 and was an ASP postdoctoral fellow in NCAR HO from 2011 to 2013. He joined the UCAR Cosmic Program as a project scientist in 2013 before returning to HO in 2016. His primary research interest is the variability and predictability of the mesosphere, thermosphere, and ionosphere, with a particular focus on the coupling of these regions with terrestrial weather. His research additionally focuses on the development and application of whole atmosphere general circulation models and data assimilation systems, as well as techniques for observing the ionosphere using space-based GNSS observations. So to Nick now.
Thank you, Masumi. And as Masumi mentioned, I talk today on development and application of data assimilation for whole atmosphere model. And before I begin, I would like to thank several people who I would say primary collaborator and contributor to this work. In Sizzle, Jeff Anderson and Kevin Rader, who help a lot with the implementation of the DART with Wacom and Wacom-X, and Hanli and Chiting here in the HAO have contributed a lot. Fazul at CU with some of data assimilation, and then some colleagues in Taiwan who also contribute with the ionosphere data assimilation. So in terms of what I will present today, I will start with some very basic as to why we want to do data assimilation for the whole atmosphere model, and then some specific challenges related to implementing data assimilation into whole atmosphere modeling, and what makes it distinct relative to data assimilation you might do in either ionosphere, thermosphere alone or in the lower atmosphere. And then I'll discuss the data assimilation implementation in both Wacom and Wacom-X, and then I will finish the talk by discussing some of the more recent work looking at the impact of assimilating ionosphere and thermosphere observations in Wacom-X. So very basic in terms of why we want to do data assimilation, since especially in HAO, it's less, and for space weather, not as common of a tool that is used. So in the most general sense, we have some numerical model that provides global information of many states, but it's always going to have some uncertainty and biased information that it will provide. And though we have many observations, they're always going to be somewhat limited in scope, both in terms of their coverage spatially and temporally, but also just fundamental limitation in terms of what they can observe due to certain limits on what just can be observed. And so really what we want to do with data assimilation is combine these two together. So we take the observation and some model prediction, combine them through the data assimilation algorithm, and then we get some corrected model state that would often be called the analysis state, and then that is what we would use for data assimilation. So this is just a general data assimilation, why we want to use it for any problem. But specifically, if we start talking about whole atmosphere model, there's several reasons why implementing data assimilation is quite important. So in order to recreate the day-to-day variation of the sort of weather, it then propagates upward into ionosphere and thermosphere. Most whole atmosphere models have historically been kind of nudged to an atmosphere reanalysis. And one of the constraints of this is that the reanalysis products typically only extend up to maybe 50 or 60 kilometers. So that means you can only constrain the very lowest levels of your model. And this then results in large uncertainty at higher altitude because the model is unconstrained. And that is shown here on the right, where this is comparison from several different whole atmosphere models, all being constrained in the kind of below, if you can see the gray line here, This is altitude versus day of year during 2009. And they're constrained up to about slightly different levels for each model and with different ways. But if you look kind of in the lower atmosphere, all of the models look quite similar where they're being constrained to a reanalysis. But once you look at higher altitude above where they're being constrained by the reanalysis product, you can see they're all very different. And the reproduction of the dynamics in the mesosphere and lower thermosphere is quite different. So by not being able to constrain that part, we have a fundamental limitation in this sort of technique of just nudging towards some external reanalysis product. And a more recent comparison show the power of using data assimilation to correct this. This previous one I show is from 2014, and then a few years ago, using a slightly different set of model, show a comparison of, this is 4 different models that then assimilated data into the mesosphere. And this is again, altitude versus time here. This is on the upper left is a model developed in the Navy. The upper right is a Jaguar data assimilation system developed in Japan. Then this is Wacom Dart, which I'll discuss in more detail, the development of later, and then also Mira 2 on the left here. And all of these are now assimilating data up to 100 kilometer rather than just nudging to a reanalysis. And look, the comparison is much better into the higher altitude domain where they're being constrained directly by the observation. So if we can assimilate data at these higher altitudes above the traditional reanalysis, this essentially just mitigates the biases in the background model to a higher altitude than you can do just by nudging to the reanalysis product. And there's several other advantages that we might get from assimilating the middle atmosphere data. This is a comparison again from the Navy model showing this is altitude versus latitude. I have 2 representations of the data assimilation model. On the left is where they assimilate data up to 100 kilometers, and on the right is up to assimilating data only up to 40 kilometers. And this shows the amplitude of the DE3 tide, which is an important sort of atmospheric tide for propagating information from the lower atmosphere up into the ionosphere thermosphere. So getting the amplitude of this tide right is quite important for then how it couples into the ionosphere. And if you look at the amplitude differences here between the left-hand panel when you are assimilating data and the right-hand panel, it's roughly a factor of 2 difference. So just by incorporating this higher altitude information, you're really getting a completely different dynamical variability in the mesosphere and lower thermosphere, which then impact consequently ionosphere and thermosphere. So we really cannot just rely on these reanalysis or lower atmosphere observation. You really need to extend to a higher altitude in order to get better representation of dynamics. And as I said, this difference impacts ionosphere and thermosphere, and that is what is shown here. So if you take these same 2 representation of the dynamics on the previous slide and then feed that into ionosphere model, that is what is shown here. So this is a mapped latitude versus longitude of the peak height of or maximum density of the ionosphere F region. Again, a case where you are assimilating all of the observation up to 100 kilometers on the upper left. And then the bottom left is if you only assimilate the observation up to 40 kilometers. And then here is the difference. And in general, on average, you'll see 10 or 20% difference in the ionosphere. Some regions are quite a bit larger. So this confirms that you really need to have a higher altitude constraint than you would typically get, and how that would then impact the ionosphere as well. So this part is kind of motivation for why you would want to implement a middle atmosphere data assimilation. There's also a reason you want to do assimilation even higher into ionosphere thermosphere. And that is an example is shown here, where on the left-hand side, this is a plot of the observed rate of change of the TEC. So it's some measure of the basically irregularities or instabilities in the ionosphere. and you can see on this stage that is highlighted the instability or rate of tech index is much higher in India compared to Taiwan. And then on the right is two instances of the TIE-GCM model, Rayleigh-Taylor growth rate with and without assimilating ionosphere observation. So the dashed line is if no observations are assimilated in this case, and over Taiwan in the red and India in the blue. And so without any observational constraint on the ionosphere, in this case, you can see it's larger in Taiwan compared to India, which is directly opposite what we're seeing in the observation. And then by assimilating observation in the, you can see in the solid line here in blue for in India compared to over Taiwan longitude sector, it now match better what is in the observation. So assimilating the ionosphere observation in this case give you a better representation of these sort of smaller scales, and then you can look into the physical drivers of what would be driving this sort of larger growth rate of instability in India compared to Taiwan by correcting it with this sort of data assimilation approach. So hopefully that gives you some reason why we would want to do the data assimilation in the middle and upper atmosphere. And so motivated by these reasons, we implemented the data assimilation in both Wacom and Wacom X. And I'll talk more in the subsequent slides as how this was exactly implemented. But it's really to get this better constraint at higher altitude than you could typically do. And the implementation was done using the DART ensemble Comet filter developed in Sizzle. And I'll discuss in some of the next few slides the extending this data assimilation from a sort of lower atmosphere only up into consider the whole atmosphere domain. This really posed several unique challenges. So the methodologies that might have been developed for in troposphere and stratosphere data assimilation cannot just be sort of directly applied and then just assume they work perfect. So there needs to be some adaptation there. And in addition to some of the examples I already showed, there's other application of the whole atmosphere data assimilation that would motivate development of this. Several are listed here. There are likely others as well. First, it can be used for initial conditions for investigating the predictability of the upper atmosphere. For doing whole atmosphere physics-based forecasting system, this allows you to incorporate variability coming from the lower atmosphere into the forecasting system. And then you can potentially use it for estimating uncertain model parameters through the data assimilation. And then last point is it could be used to generate essentially a reanalysis for the whole atmosphere. It could be used for both scientific study as well as potentially training machine learning models. So as I said, there are several challenges for developing a whole atmosphere data assimilation system, several of which are listed here, and I'll go into the first four in more detail in a few slides. The first challenge is that the evolution of the system is due to both internal dynamics as well as external forcing. So it's some combination of being driven externally and then also the initial condition. The second is that the variability in the middle and upper atmosphere occurs on shorter timescales than it might occur in the troposphere and stratosphere. Wave-driven variability is extremely important in terms of how it drives the dynamics, and I'll discuss how this needs to be addressed. And then there's also a constraint on the observing system, which is just less well developed compared to what you might have in the troposphere, stratosphere, meaning that you just have much sparser observations to sort of constrain the model state. And the last point here, I won't discuss in more detail later on, but it's worth at least mentioning it. The experiments to do data assimilation of the whole atmosphere model are relatively expensive. And that just has some implication in terms of how much you can sort of continue to refine and develop the technique, because you can't run a sort of infinite number of experiments because each one can be quite costly in terms of computational expense. So that places some constraint on the sort of development that can be done. So the first problem that need to be addressed is the fact that the ionosphere and thermosphere is sort of a partly driven system. And by that, it means it's driven both by the external forcing from the sun, but also internal dynamics. So in sort of, you can think of two types of system. One would be a kind of chaotic system, where if you just start with your state slightly separated here at the initial time, and you propagate the state forward to some future time, it's almost entirely controlled by the initial condition, right? So some small difference in the initial condition, then in the future it diverge, and that's kind of independent of how you might force it externally. And the opposite of that would be a strongly forced system, where you, no matter where you start, if you apply the same forcing, you kind of end up in the same place. And so you can think of this sort of spectrum along between these two. Some systems are kind of highly initial condition dominated, and some might be more forcing dominated. So numerical weather prediction in a kind of classical sense more is tilted towards the initial condition dominated framework, where you rely on the sort of difference in initial condition to create your ensemble spread. And ionosphere thermosphere is a bit more of a partly driven system, where the external forcing plays a role in how the system will evolve. And if you wanted to, some other examples of maybe more forcing dominated doing, say, climate prediction or magnetosphere, data assimilation or projection is more of dependent on how you want to specify the external forcing. And the initial condition may be less relevant to the ultimate end state. But so because it is initial condition, not solely dependent on the initial condition, that means you have to treat this sort of external forcing when you're developing data assimilation system. And so to do this, we try to, if we don't account for this, the ensemble spreads ends up being too small within the data assimilation, within the ensemble used for data assimilation. So here are just several example profiles of the electron density at different location, two different locations, one in the equatorial region on the left, and then on the right is at mid-latitudes. And there's a case where you don't include any sort of spread in your external forcing. So the external forcing is all the same for every ensemble member. And then the other ones include the forcing spread that we implement to improve the effectiveness of the data assimilation. And you can see without accounting for any forcing spread, the ensemble spread can be quite small at different altitudes. So here is with no spread in the forcing, there's still some variability due to the lower atmosphere effects. But then if we account for the forcing spread, we get a much larger spread within the ensemble, so the data assimilation can be more effective. And that's shown here in this example on the left-hand side, and here is on the right is at mid-latitude. And again, you see if we don't account for this sort of contribution from the external forcing, you get a very small ensemble spread, which can inhibit the effectiveness of doing the data assimilation.
Question. So does forcing spread mean uncertainty in the forcing? Is that what that means?
It's not necessarily strictly uncertainty. It's a way to sort of create some spread in the ensemble. It's a little hard how you would want to trade it to uncertainty, because how you want to trace it back. For example, what we do here is we apply F10.7 spread. And strictly speaking, the uncertainty probably on the F10.7 measurement is very small. But how that propagates into the actual model, you could argue that there should actually be some spread in F10.7, because even though the value is known, how that translates into, say, a radiance is not known to the same precision. So it's not strictly uncertainty. Does that answer your question?
Kind of.
And to some extent, it is a little bit of an artificial way to create spread that's been developed. It's maybe not the best approach, but it does help create this sort of spread in the sort of driving parameter. Mm-hmm. And so, so to address this sort of need to get larger spread than would be just from the internal dynamics and the contribution from forcing spread. In the WACOM-XR, we incorporate this extra sort of forcing perturbation from the F10.7 KP, and then also the nighttime O+ flux coming in at high altitude. So the other aspect that is quite different in middle and upper atmosphere data assimilation is that the timescales can be much faster than a sort of typical 6-hour data assimilation cycle. The two examples here showing the more sort of fast pace of dynamics. On the left, this is at a lower altitude range, say 80 to 100 kilometers, and this is time. And this is coming from observations of LiDAR observation of temperature. And you can see there's very kind of quick and highly varying dynamics. So to capture this sort of variability, if you use a long data assimilation cycle, like a 6 hours, you would be missing a lot of these sort of variability. And on the right is more example on the ionosphere variation. And this is hours now on the x-axis and latitude. This is the total electron content in ionosphere. And there was a storm here at this time, geomagnetic storm. And you can see from, say, 24 to 30 hours over a 6-hour window, there's rapid variation in ionosphere. And so using a long data assimilation cycle would be challenging if you want to capture these sort of rapid evolution. So to address that, we shorten the data assimilation cycle in WACOM-X and WACOM to a 1-hour data assimilation cycle so we can capture the faster timescale. And then another specific challenge for whole atmosphere data assimilation is the treatment of small scale waves. And this is a significant issue, especially once you start to go over the entire atmospheric domain, because there's essentially two issues. First issue is that the gravity waves, so the smaller scale waves, are they're an important source of the dynamical variability. So they need to be incorporated into the model and considered in terms of how they drive the variations in ionosphere and thermosphere. But the other issue is that when you start doing data assimilation adjustments in the lower atmosphere, this can essentially introduce spurious small-scale waves. So by doing the data assimilation, you could create additional wave that then has negative effects on your whole atmosphere system. But you can't just kind of excessively damp out this potential noise because you need to preserve the actual real wave variability. So there's a significant balance here between not trying to remove too much of the wave variability and dealing with the fact that you might be introducing some additional wave variation. And this mixing introduced by these small scale waves can actually have a pretty significant impact on the ionosphere and thermosphere. And on the right here is an example, just focus on the black and sort of orange line. And so the black line, this is over a year, but the point I think can be made that in the black line is a standard run of the time GCM model. And this is a variation in the total ionosphere, total electron content. And the orange line is if you just remove the gravity wave forcing. So if you compare the black and orange line, they can be 20 or 30% different. So this sort of gravity wave contribution to ionosphere is quite significant. So if you're either adding way too much gravity wave, that's essentially noise from the data assimilation, you're going to really reduce the ionosphere density. And if you just damp too much, then you don't have enough sort of variation. And that's also going to be problematic. And as an example of how this is sort of in practice, here is some examples of when the data assimilation was first being developed. So this shows an F region maximum ionosphere density. And there's 4 plots here. The upper left, so these are all latitude versus longitude. Upper left is WACOM-X with no data assimilation. So what we would get for the ionosphere if it's just kind of left by itself. And then the upper right, this was one of the first attempts we tried to do data assimilation in the whole atmosphere. And you can see without any sort of adjustment, instead of being an ionosphere that looks like this, it shrinks by kind of over half. And this is because we were introducing a lot of kind of extra variability in the model, and that just sort of shrunk the ionosphere. And then the bottom panels show an example, two sort of tests of how we dealt with this issue. The bottom right is if we just modify the sort of divergence damping within the model itself. And you can see if we just make that change, it gets closer to the kind of default, but it's not quite there yet. And then on the bottom left is if we adjust the model damping and the data assimilation inflation, which kind of helps reduce some of this noise. So really being able to address this sort of small scale wave is kind of a balance between trying to prevent too much introduction of small scale wave, but also preserving the real wave variability. And this is a challenge that's kind of unique to whole atmosphere data assimilation, because as the waves go up to higher altitude, they're going to grow in amplitude and their consequences will be larger. So really dealing with this problem is unique to this issue of whole atmosphere data assimilation. And so the last kind of major issue for whole atmosphere data assimilation is the fact that middle and upper atmosphere observing systems are less developed compared to the lower atmosphere. Here is an example showing middle mesosphere, lower thermosphere observation tracks. And then on the right is the stratosphere, troposphere observation. So you can see there's a lot more sparseness here in terms of what we can observe compared to in the troposphere. So this essentially just means you need to make most effective use of the available observation. It's really critical to use them effectively. And then the other issue is that in the ionosphere, and thermosphere, there's significantly fewer thermosphere observations compared to ionosphere, but the thermosphere kind of control the state of the ionosphere. So just changing the ionosphere from this dense observation doesn't really give you much, because it's a thermosphere that is sort of driving those variations. So those are some of the challenges and the kind of implications I summarize here. So first, the shorter timescales require a more rapid data assimilation cycling. We need to account for the external driving when generating model ensemble. This issue of the small scale waves is quite unique to whole atmosphere data assimilation, and you need to essentially mitigate this generation of artificial small scale wave, but also preserve the real waves. And then because of a limited observing system, need to make the most effective use of the available observation, and then also accurately represent this covariance between ionosphere and thermosphere to leverage the ionosphere observations. So all of these things have been addressed to develop this Wacom and Wacom-X Dart data assimilation system. And this is what we develop, and it can assimilate the observation truly extending now from the surface all the way up to 500 kilometers. And on the right here is a distribution in altitude of the different observation that can be assimilated in the model. So in the lower atmosphere, we can assimilate the standard meteorological observations. And then in the mesosphere, lower thermosphere, temperature observations from Aura MLS and Time Saber. And then in addition to that, ionosphere thermosphere observation can now also be assimilated, which is from the ionosphere data, from radio occultation electron density profiles, and then ground-based GNSS TEC data, and then also data from gold temperature, and then ICON, MIDI, neutral winds. And this data assimilation system that was developed was really the first time that it could be all done in one model to assimilate from the surface all the way to the upper thermosphere. So this was the first one developed, and I think actually maybe still the only one that can do this all seamlessly within one model framework from surface to high altitude. And so now I'll show some of the results in terms of how both sort of verification of how well the model does, and then how it improved the representation. So this is just verifying in the troposphere how the model performs. This is two snapshots of the geopotential height at 500 hectopascal on two dates in November 2008. The top panels are from NCEP, the reanalysis, and then the bottom is from Wacom DART. And you can see if you compare the NCEP result in terms of the large scale feature with what we have in Wacom DART, it's generally reproduced the sort of large scale structure that you see in the NCEP reanalysis, and then also the variability from one day to the next that we see in the reanalysis is also captured in the Wacom DART data assimilation system. So we have some confidence that we're kind of reproducing much of this sort of large scale feature in the troposphere that would be seen in the reanalysis. And then if we go to higher altitude, you can see that it starts to remove these sort of biases that is inherent in the background model. So this is looking into the lower thermosphere. This is latitude versus longitude for a snapshot. The upper left here is if only the lower atmosphere observation are assimilated. And then the upper right is assimilating observation up to, say, 100 kilometers. And then on the bottom are the observations that went into the data assimilation at this altitude level from Time Saver and Aura MLS. And if you see in that, when we don't assimilate any of these data, it's kind of the reddish color to yellow. So there's this bias relative to what you see in the observation. And then when the data are assimilated, you get a sort of blue to green type of color, which is much more closer agreement with the observation. And one thing you can see here is it's the impact sort of builds up over time. So it's not restricted just to where you had observation. So it removed the bias sort of with some sort of length of time. It doesn't go back kind of instantly. So it isn't just removing right where you have the observation. So this helped mitigate the sort of background bias in the model in MLT altitudes. And then it also captures much of the sort of shorter term variability in terms of tides and planetary waves. On the left, I apologize, this is a bit of a busy figure, but it's essentially comparing radar observations in red, NavGem, which is this Navy high altitude data assimilation system, and then Wacom in green. And this is over about 15 days in December 2009. And you can see, generally speaking, Wacom agrees with the observation reasonably well. There's time period when it doesn't agree perfectly. This is, I should say, independent observation. But other sort of data assimilation model are also have some disagreement. And on the right is looking at the quasi 6-day planetary wave, so a larger scale planetary wave, again, comparing Wacom with data assimilation in the top, and this is over a year. And so you see there's times when the planetary wave becomes enhanced in the data assimilation system, and that is in good agreement both in sort of the time period as well as the magnitude of the planetary wave variability in the model data assimilation system is in good agreement with the observation. And then because it is in good agreement, you can then look more into the physical mechanisms sort of creating these enhancements of the planetary wave activity. And so this is another example showing how the assimilation of the middle atmosphere observation in Wacom XDART can improve the representation of dynamics and transport. So this is altitude versus day of year. And the upper left here is when the model is only constrained up to about 50 kilometer. And then the bottom left is constrained up to 100 kilometer. And you can see that the dynamical variability compared to the observation is in much better agreement. And then this has implications for the dynamics and transport in the MLT. This is a NOx in the SD Wacom where it's not constrained to high altitude. And then the bottom left is constraining it to a higher altitude. And you can see that it's a much deeper sort of descent of the NO in Wacom star compared to SD Wacom. And this is more consistent with what we have in observation. And then these differences impact the MLT dynamics and ionosphere variability. Here is showing local time versus day of year. Again, this is a vertical plasma drift in the ionosphere, equatorial ionosphere. Perturbation, if we constrain only up to 50 kilometers versus constraining up to 100 kilometers. And then on the bottom is observation. And you can see the day-to-day variability in the model where we constrain to higher altitude in ionosphere is more consistent with the observation compared to when it's only constrained up to 50 kilometers. So in this model, we can get better representation of ionosphere. So now I'll discuss some of the more recent work on assimilation of the ionosphere-thermosphere observation. Three aspects. One, impact of assimilating ionosphere observation on thermosphere and neutral density. Then the impact of Icon Mighty neutral wind assimilation. And then last, the assimilation of gold neutral temperature. So to look at the impact of the ionosphere observation on thermosphere neutral density, we perform some Wacom star observing system simulation experiment. And in these cases, the sort of run of the data assimilation is performed with a biased ionosphere and thermosphere relative to our truth or nature run. And this results in a thermosphere that is shown here. This is a neutral density at 400 kilometers. Here is the nature run that we're trying to recover. And then we run the data assimilation with a background that looks like this. And then we're trying to basically adjust towards this state using only ionosphere observations. And this is a neutral thermosphere. And so 3 experiments are performed, 1 with no ionosphere data, and then 2 assimilating the ionosphere data in different ways in terms of how the ionosphere feeds into the thermosphere. And these experiments will provide some insight into how the ionosphere observation can improve forecasting and specification of thermosphere neutral density. So here is just a look at how the ionosphere is improved. Here are synthetic observation maps on the left, and then the different case of assimilating ionosphere data. Without assimilating the data on the left here, you can see the analysis state and forecast is far from the observation. And then once the ionosphere data are assimilated, you can see the short-term forecast and analysis are in better agreement with the ionosphere. So we're essentially getting a good representation of ionosphere from the ionosphere data, which is kind of what we would expect. So it's more interesting to look then into the thermosphere, but this just confirmed that the ionosphere is being correctly reproduced. And here just show the sort of statistics that the root mean square error for ionosphere reduction and bias are improved by about 17 and 12% when we do this sort of data assimilation. So looking at the thermosphere, the way we can do this adjustment is essentially we rely on the covariance information between the ionosphere and thermosphere to then adjust the sort of non-observed state of the thermosphere from the ionosphere. So if we have some observation of, say, total electron content, and we want to adjust the model state, we can rely on the ensemble covariance to determine the adjustment, say, to the thermosphere from this ionosphere state, and then we can look at how well that performed. So here are the different experiments. This is neutral mass density maps at 0 UT. And so the upper left here is the truth that, again, was biased relative to our data assimilation. And then here on the upper right is when we don't do any ionosphere data assimilation. And you can see there's a clear bias between this case and the truth. If we just impact the ionosphere with the ionosphere data, there's still this large bias in the thermosphere neutral density you can see. But in the bottom right, when we allow the ionosphere observation to then impact the thermosphere, you can see that this total bias, that not completely, but the bias start to go away relative to the truth. So the ionosphere data is kind of improving specification of the thermosphere neutral mass density. And this is show the percent error of those previous plots. So again, with no ionosphere data assimilation, you have errors on the order of 40 or 50% in the thermosphere neutral density. And then once we assimilate the ionosphere data and allow it to correct the thermosphere, we reduce the error in the thermosphere neutral density to closer to maybe 20% or 10 to 20%. So a significant reduction in the error relative to if we, by leveraging this sort of ionosphere data. And if we look at the root mean square error to get a slightly more quantitative assessment, here is the root mean square error globally at 400 kilometers for the cases of no assimilation and with O plus only impacting the ionosphere. And then on the bottom is if we assimilate and impact the thermosphere. And you can see that there's about 50% reduction in the root mean square error by leveraging this sort of ionosphere data to correct the thermosphere. And this is kind of consistent with what we had, what has been shown previously with just the TIE-GCM model. And an interesting question is, how does this translate into forecast? And so if we initialize a forecast here on the 17th, and then the dashed line here is the forecast. So by doing this sort of state correction of the thermosphere, you get something like a 24-hour sort of improvement relative to if you just did nothing. So even though we're driving it with a biased sort of forcing in the thermosphere, if we correct the thermosphere state based on the ionospheric driver, you can potentially improve the thermosphere neutral density forecast out to about a day in the future, even with sort of imperfect knowledge of the external forcing that we apply in this case. So next area I would like to show is the ICON MIGHTY neutral wind assimilation using the so-called empirical localization function. And so MIGHTY instrument measures the neutral winds in the thermosphere. And we performed two sort of assimilation experiments. And this kind of show how you can use different approaches to sort of get the most value out of the observations that you have. So there's different ways you can localize the impact of the observations onto the state, and that's sort of control the extent spatially that the observations are going to impact your state. A normal approach might be just use some sort of quasi-Gaussian distribution, say in latitude, longitude, and height, and that could limit the sort of utility of the observation. In this approach, we use the empirical localization function, which then allow you to get maybe more powerful impact of observation. So these figures show the empirical localization functions for different altitude regimes in the lower thermosphere, in the sort of middle thermosphere, and then in the upper thermosphere. And these, if you look in the upper thermosphere, this localization function is highly kind of asymmetric and extends much higher in altitude than it does in lower altitude. Whereas in the lower thermosphere, they're sort of more contained in and much more symmetric. And what this means is that in the upper thermosphere, when we assimilate using these empirical localization function, the impact of the observation extends much higher in altitude. So you're not sort of cutting off the impact based on just using a sort of restricted localization. You allow it to sort of stretch in altitude and hopefully have a greater impact then on the model states. And if we look at the root mean square error in the model, when we compare these different localization, a sort of confined one that's this Gasperi cone that is more Gaussian-like versus this empirical localization function that extend the impact, you can see that the assimilation with the empirical localization function for the root mean square error is reduced compared to if we just use the Gasperi cone localization. So by sort of using more sophisticated technique in the data assimilation, we can really extend the impact of these limited observation systems. And this is the root mean square error for the neutral wind. And interestingly, this then has an impact on the ionosphere vertical plasma drift. So here, this is day of year versus local time. The left is our known truth for the vertical plasma drift at the equator. And then here are the two cases of the data assimilation of this icon. observations difference relative to truth. So this is essentially the error. And here with the sort of more impactful observation with this empirical localization function compared to the standard localization function, you can see the errors tend to be reduced. And it turns out it's about 7% improvement on average. So this shows that sort of, if we do have this kind of limited observing system, there are techniques we can develop to kind of improve the impact of these observations through sort of better impact of the observation. And then the last topic I'd like to discuss is the assimilation of the gold disk temperature observation. And so I think most people know that the gold instrument is a far ultraviolet imager in geostationary orbit, and it provides a disk image of composition and temperature in the daytime, and then 1356 radians at night. And here we actually investigate the impact of assimilating real gold observation on the thermosphere composition, and then also ionosphere electron density. So again, we're using observation of temperature, and we want to look at how it can improve other states of ionosphere and thermosphere. And one of the things to mention, gold is also a complex data set to observe because it's sort of looking down at the disk. So you have to account for how you want to localize these observations and the contribution function. So on the upper left here is the contribution function for different solar zenith angles for this radiance. And then on the bottom left is what was actually implemented in the data assimilation. This dashed red line, which is a kind of fit empirically to these known contribution functions. So that's how we do the essentially forward operator. And then to localize the observation, we again have to do something where we kind of extend the impact up into the upper thermosphere and cut it off at the lower altitude because it really isn't providing equal information above and below the sort of peak altitude of the contribution. And here are some of the results when we assimilate the gold data. This is root mean square error with respect to the temperature. So here, this is kind of with respect to what you're assimilating. So you obviously expect improvement. But more interesting is on the right-hand side when we compare with the thermosphere composition. And so the blue line here is with no data assimilation. And then the red is the data assimilation kind of done in a not ideal way where you only allow the temperature to impact the temperature in the thermosphere. And there you can see the error grows and is comparable almost to what you would have if you don't assimilate any data when it comes to composition. But if you allow the temperature observation to then impact the thermosphere composition, we can get significant reduction in the error of the thermosphere composition, about 30%. And this is true even during the geomagnetic storm time. And then also just getting the better composition from the temperature can also improve the relative to ionosphere. Again, if we assimilate it correctly, we get a much better improvement. So this shows the root mean square error on average versus latitude. Again, the blue line is without any upper atmosphere data assimilation. And then the red is this sort of optimal data assimilation where we allow the temperature observation to impact ionosphere and thermosphere composition. And we get a reduction then in ionosphere from assimilating this thermosphere data as well. So that is the last of the main result I'd like to show. And in the last few minutes, I'll just summarize and discuss some future work. So as I mentioned, whole atmosphere data assimilation really presents some unique challenges relative to sort of data assimilation if you're going to do only in the lower atmosphere, or also if you just wanted to do standalone ionosphere, thermosphere data assimilation. There's some difference if you really want to go to the whole atmosphere, but it's actually quite powerful, and implementing data assimilation can improve representation of composition, dynamics, electrodynamics in mesosphere, thermosphere, and ionosphere. And by doing it throughout the whole atmosphere, you can really look at these sort of coupling between the different layers in a better way. And the results I show, I think, demonstrate that ionosphere observation can can improve the specification and forecasting of the thermosphere neutral density. And then also, if we assimilate effectively thermosphere observation, they can also improve the ionosphere as well. And in terms of some of the future direction and kind of outstanding challenge for whole atmosphere data assimilation, there's still some discussion in the field. As I mentioned, that the state is partly externally driven, and one approach to doing data assimilation for upper atmosphere is use your observation to just estimate the drivers and not the state. And so you would just assume it's externally driven, and you change your driver and let the model take care of the state and don't change it. And really understanding the advantage or disadvantage of doing state versus driver estimations and how they could be used for different problems or even combined together is a significant problem that has not really been explored. I showed some examples of how to make the most effective use of these sort of sparse data. But I think there's still a significant area where this can be explored in more detail. And this method for generating ensemble spread, as Bill asked earlier, could be better, I think, in some ways in terms of how it is done in a more realistic manner, taking into account true uncertainties. And we still have some areas that we struggle to get sufficient spread because the drivers may be ineffective. And then other areas that I think are important to look at is to quantitatively evaluate the impact of different observing systems on sort of specification and forecast, as well as their combination together. And last, using these sort of initialized hindcasts to truly investigate in detail the predictability of ionosphere and thermosphere. So I will conclude there and then can take any questions you may have. Thank you.
Thanks, Nick, for excellent talk. It's open for questions, and online participants, you can either raise your hand or just unmute and ask your questions.
So coming from a kind of place of ignorance on this stuff, I assume that the ideal end goal here is to not need to do data assimilation at all, but you get your models to the place where they work, right? So my first question is that true? Or is it actually computationally cheaper to do the data assimilation compared to increasing complexity in your models? I have a follow-up. Okay. So my follow-up question is, if it's true and you do want to use, can you use this work to look at where you want to improve the models, where the models are failing?
So I'll answer both at the same time. Well, actually, I'll answer your second question first. So one application of data assimilation is whenever you do the data assimilation, you basically see adjustments. So you say, here was what I observed, and here was what my model said. So I needed to adjust this much. So you can create maps or profiles of where you have the largest differences, and then you could use that maybe to guide where you should be putting your effort as to where the bias is. And you can also potentially do, say, parameter estimation. Say, I have some uncertain parameter in my model that I use for tuning. I'm going to use data assimilation to estimate that. That area is less explored in terms of how effective that could be, but that's one thing you could potentially do. And your second question is, I guess, more of a philosophical, or your first question, more philosophical of, would you want to, or could you get to the point of your model is just so perfect that all you have to do is provide the right boundary condition and it's going to get everything right? And I guess you could maybe think that that would be an end goal, but it's maybe unrealistic to think that you would ever get to a point that your model is so good that you wouldn't want to be sort of adjusting it to match what you observe. That's maybe my opinion. Right, I think assuming that your model is always going to have some errors and biases is probably a reasonable thing. to assume. So then you would kind of always want some data assimilation to sort of be correcting that.
Mike?
Hey, Nick, thanks for a great talk. Just a question to explore a little bit more about the way you got the variance in the ensemble and how broadly you can extend that. I completely agree with your description of the magnetosphere being one of these highly forced systems. And back in the day when we were trying to play around with that forcing really makes it hard to do data assimilation that's in there. So can you extend the approach that you have gotten for the sort of the middle tier system to a system that's more strongly forced? And how do you decide how much variation and variability to put into that input to get the spread that you need?
So the second question, how much variability, that's probably maybe more of a art part where it's, you kind of do some perturbation and see that you get sufficient spread, which is, you're kind of looking at the end result and saying, well, I need to have this much spread for the data assimilation to work. So you need to adjust the driver in a certain way. Your first question, if it's strictly a driven system, this is where driver estimation is maybe more what you would want to be doing. So for something like magnetosphere, you could think of, say, I have my set of magnetosphere models all driven by slightly different, upstream solar wind condition, and they're all going to be different. And so based on, some comparison of my magnetosphere model with observation, which of these upstream drivers is best? But they're given the expense of magnetosphere models, that's probably not trivial to run, 40 instances of your magnetosphere model with slight variation, but I could see how that might work for magnetosphere in that way.
Yeah, thanks.
Sarah and then Michael.
Yeah, I think my question is related to the last two. I'm just trying to get a sense of the nature of whether it's a driven system or the nature, or either you're even in a chaotic system. In a case like that, you really could never get to the point where the model could solve it, right? Because you could never get a perfect boundary condition or a perfect initial condition, or am I being naive about that?
Well, again, this could somehow be a bit of a philosophical question of like, if it is a strictly driven system and your model was perfect, I guess if you had perfect external, right?
But is
There's always some,
it's not strictly driven?
No, in ionosphere thermosphere, it's not. And I mean, that you can see, if I go back a few slides, like the initial condition does matter for some time period. Here, right? So if we just stop doing data assimilation and it's driven by this, over a day, it goes back to that state, but it's not, right? It has enough time lag that the initial condition does matter to some extent.
Michael, could you hold on a little bit? I take Joe's question. Joe, you had a question, right?
Well, it was related to the others in terms of this issue of getting the, I think the words were the spread you need in the ensemble system. And my question is, I guess, how much spread should there be if it is highly forced, and if the uncertainty in that forcing is much less than the spread that's put into that forcing in order to get a significant spread? Maybe ensemble techniques aren't the best data assimilation approach.
Yeah, that is a good question. So the amount of spread is somewhat, dependent on being able to capture the full range of variability. And the question on how much uncertainty you put into the drivers is a little bit difficult for several reasons. Strictly speaking, the drivers are well known, but how those drivers translate into variability in the model is not known to the same extent. I don't know if that what I'm saying makes sense. I think, for example, Bill's question with the solar irradiance, you might know the value of solar irradiance quite well, but how that translates into, say, your actual, chemistry within the system introduces additional parameterization. Or for the high latitude forcing, the KP index, we might know the value of KP quite well, goes into your, precipitation at high latitude, and your electric potential is actually quite uncertain. So to some extent, it's somewhat valid, I think, to say, well, even if that value is known completely, there is still uncertainty once it propagates through the system.
Okay. That's very nice talk. Thank you.
Michael and then Julio.
Yeah, I take from the discussion that the system is overall stable and then follows day, night, and annual variations. And you are studying how the system reacts to short-term disturbances of unknown quality, because the measurements of what kind of a disturbance comes is sparse. Now, and then you see that there is more or less, in some instances, random behavior of the system with some larger variations and sometimes not. So it brings me to the question, you have worked with this for a long time now. What is your feeling? What the greatest inherent uncertainties in this overall model are?
I'll just have one clarifying, in the data assimilation system or the background model?
In
So-
the background
Okay.
model,
In
the way the physics and the chemistry are being described, but also in, I don't know, mathematics.
Okay. So in the background model itself, one of the biggest issues, especially in the sort of middle atmosphere, is the parameterization of gravity wave. In the kind of second or third slide I showed, where they just constrain to kind of say 50 kilometers, and then there's huge difference at around 100. That's all mostly due to just how these gravity waves are parameterized. That's a huge uncertainty in that part of the model. And then that does actually have some impacts at higher altitude on the circulation as well. So that is one of the things that's kind of being corrected out by this sort of background bias.
So with parameterization of gravity waves, you mean that you don't resolve them in time or in space?
Essentially, they're occurring at a scale that is below the grid scale of the wave. So they need to be parameterized because they can't be resolved.
Julio.
Hi, thanks, Nick, for the great talk, and apologies for keeping you over. I also had a question about gravity waves. You were mentioning the contradiction of, wanting to preserve gravity waves from below that are forced maybe realistically, and the ones that are being forced by your assimilation process. I was surprised that you think the I assume you were talking about resolved gravity waves coming from the lower atmosphere, and I'm surprised that you have any any faith in those at all. I'm wondering what it is you want to conserve about them.
Yeah, so maybe I didn't phrase everything correctly when I said it. So there is the issue of being too sort of heavy-handed on the damping is that then it kind of leaks into, say, tides that you actually do want to preserve and that you do have faith in that they're correct. But I would agree with you that the other smaller scale you may not trust. But when we try being kind of too strong of damping, ended up negatively affecting some of the larger scale waves that we would trust. Does that answer your question? And I apologize if maybe that was not clear when I sort of first said it.
Yeah, that answers my question. Thank you.
Valerie?
Nick, thank you for a great talk and a lot of information and useful results for future. So just one comment. It's not only a force system, it's also highly dissipative system. And so 1 hour data simulation still is larger than dissipative scale due molecular viscosity. That's why you probably need a large ensemble spread to accept the data. This is another interpretation about why you need ensemble spread at the top, in the top of layers. Because time scale for molecular dissipation seconds comparing to data simulation 1 hour. So you have quite a fast adjustment. Thank you.
Thanks for your comment.
One more?
No. It's just I would like to
Okay.
hand down.
Okay. Komal and then Michael.
I just have a basic question. Is it possible to use ground-based data to constrain
Yes.
models? Oh, okay.
Yeah, there's no, and in fact, the ionosphere data that was used here is mostly ground-based TEC data.
Oh, yeah, GNSS. Yeah.
Michael, then
My naive interpretation of how strong the impact of these gravity waves can be was our balloon flights, where it absolutely mattered what the weather and the terrain was that we were flying over, how challenged the stability of the pointing was. Greenland mattered. Quite a bit.
Yeah, they're certainly large and important for many reasons.
You mentioned that there's adjustment in both the model damping and the data simulation. So I wonder if that would be consistent for like when you're simulating the same data set from the same instrument, like for the different period of time, basically that for different experiments, would that be consistent adjustment?
So the adjustment we apply are the same for all time. Whether you could kind of get away with or have different settings for different time periods, probably based on the sort of dynamical variability that's occurring at that time. But that would require some sort of adaptive way to sort of adjust these, which hasn't been implemented. But I would think that there's times when you might be, where you could get away with sort of a different set of settings versus other times, yes.
But when you try to assimilate like different instruments, are they still the same, or are the adjustments still the same, or is
Yes. It's the same for every sort of observation.
Like another separate question is how difficult it is to combine all different instruments. Like I would assume that it may be easier to combine global measurements, like together, but it may be like for the cross scale combination might be more difficult.
Yes, that is true. But even for global observation, if there's biases between observation, then you have to deal with those. Or if, somehow you're observing one parameter and another parameter and they're not consistent in some way, there's other sort of complication, even global. So treating sort of multiple observation does also present, its own challenges.
So that would be the ideal world, right?
Yeah, of course. Ideally, you're combining as many observations as you can.
And also
And,
different parameters,
yes,
like
yeah.
temperatures, wind,
Of course.
pressure.
Okay, it looks like if there is no other question, then let's thank Nick again.